All right, hey guys. So I'm recording this so that you can watch it whenever you need to, but we are going to start our next unit, Unit 3, on the periodic table, as you can see. And so we're going to go through, this is going to be part 1 of the notes, and so I'm going to go ahead and get started. If you're in class, make sure you grab some notes from here. And if you are online, make sure that you have Google Slides or you have some notes printed off where you can follow along, okay? If you don't like doing the Google Slides, you can take notes. You can write down stuff as you go. You can pause it if you see a slide. You can pause what you're doing. It doesn't matter, okay? So I'm going to go ahead and get started. All right, periodic table. We know a lot about it, okay? It's really, really, really important. It helps us do so many things. And so we're going to talk about kind of how it got started, okay? So the first person to create this, that we attribute this to, is a guy named Dmitri Mendeleev, okay? Some people will say Mendeleev, but essentially he is the one. The periodic table is an organization of all the elements, right? All the elements that we know of. And so in 1869, that was a long time ago, Dmitri Mendeleev, Dmitri Mendeleev, he produced the first periodic table, okay? He put all the elements with similar properties in the same horizontal rows. So he said similar properties, horizontal rows, okay? And he did it according to mass, okay? So his periodic table was based on horizontal rows, and it was according to mass, all right? And so this was his periodic table. You've got a copy of it in front of you right here on your notes, okay? And it looks kind of funny, right? It's not as nice and clean looking as ours, okay? You can see a lot of the same elements. There's not all of them, but a lot of them are there. And you can see that they have mass. Notice how his mass is not very accurate, right? Some of them only have 2 sig figs, or zirconium only has 190, right? It's just that he didn't know, right? He didn't have the precision in his instruments to be able to find out, and the accuracy. So he's even got some question marks. He doesn't even know what they're called, right? So this is definitely a useful piece of information, but it wasn't until another guy came along that kind of changed it a little bit, or a lot of it actually. And so in 1913, Henry Moseley developed the concept of atomic number. Okay? He came up with the idea of atomic number. And so this fixed a few problems with Mendeleev's table. Okay? And so through this, he came up with the periodic law. The periodic law says when elements are arranged in order of increasing atomic number, their physical and chemical properties show a pattern. So we can see some properties if we look at it in this direction. By using atomic number, we actually see some chemical and physical properties shown in a pattern, okay? So, here's what we found out. Elements with similar properties are aligned in, vertical columns called groups or families. And we talked about this last unit, okay? The horizontal rows are called periods. right? So, and there are 18 groups and 7 periods. All right. Elements in a group are similar chemically. They are similar, okay, and physically, because they have the same number of valence electrons. And I've mentioned this already before. Those valence electrons, they're the ones that are actually giving them their behavior. And so because they have the same number, they have similar properties. Elements in a period, right, so the horizontal rows, they're only similar in the number of energy levels they have. Okay? That's it. So, the first period, first row, has 2 elements. Second and third periods have 8. Fourth and fifth have 18. Sixth and seventh have up to 32. And notice the correlation of these numbers to the number of maximum electrons in each shell, right? Very similar. Okay? All right, also notice that the lanthanides, remember that's that 4F row, 57 through 70, they actually fit into the 6th period, and the actinides fit into the 7th period. And so we're going to learn in just a second how to classify elements as metal, non-metal, or metalloid using what we call the stair-step line. Stair-step. Okay? I also want you to know how to use the periodic table to tell, to tell, I lost my place. To tell what state an element is in at room temperature, and whether or not it is synthetic. All right. So, what do I mean by that? Okay. If you look, I don't have my periodic table yet, so it's a little difficult. But if you look on most periodic tables, ones that have color, especially like the one on my back wall, you'll see that some of the letters are different colored. Most of them are black, but a few of them are blue. 2 of them are blue. Well, there's a few extra that are blue. I'm not sure why those are, but there are 2 that are blue, and then there are a few of them that are red. And you'll see the red ones are actually gases at room temperature. The blue ones are liquids at room temperature, and the black ones are solids at room temperature. And then you'll see some of them, they only have an outline, and those are synthetic. That means that we had to actually make them in a lab. We don't find them in nature. And so pretty much every element after uranium, after 92, is a synthetic element. We don't find it, we just made it. Okay? And then you'll see like 43 technetium, whatever it's called, it's also synthetic. We don't have an element. We don't find that in nature. All right? I'm just going to kind of reiterate the names of the groups. We've already talked about those. You already have them written down. So remember, group 1, those are the alkali metals. Alkali, so no line. Number 2, those are the alkaline earth metals. Okay. 3 through 12, those are the transition metals. 13, that's the boron family. Just gonna put fam. 14, that's the carbon family. 15 is the nitrogen family. I'm just gonna put M, you know what I mean. 16 is the oxygen family. 17, those are the halogens. 18 are the noble gases. 57 through 70, those are the lanthanides. And then 89 through 102, those are the actinides. Okay? And you already have all these written down from last unit, okay? All right, so metals, nonmetals, and metalloids, okay? All elements can be classified as one of these three, okay? So we see here on this periodic table, and you don't have one on your notes. Well, you do have one on your notes. You have this one, and so you can see that there's an overwhelming majority of metals, right? Most of them are, okay? And so this is that stair-step line I was talking about, okay? If you look, this is boron, this is aluminum right here, okay? And so that stair-step line, it cuts through right here between boron and aluminum. It just goes down, right, down, right, down, right, and it continues to go down, okay? And so everything that touches that stair-step line on a side or a base, okay, is a metalloid. Metalloid, okay? There's one exception to that, and it's aluminum. And you know aluminum is a metal, right? It's shiny. It can bend, right? We'll talk about some of those properties. It's a metal. So everything that touches it besides aluminum is a metalloid, okay? Everything to the right of the stair-step is a non-metal. Everything to the left of the stair-step is a metal, except our friend hydrogen here, okay? Hydrogen goes with the nonmetals. It's not a metal, okay? At room temperature, hydrogen's a gas. There are no metals that are room temperature gases, okay? So that's one exception to remember, okay? Metals. Let's talk about some properties. Metals lie to the left of the stair-step line. They have something called luster, which means they're shiny. They're usually solids at room temperature. The only one that's not is mercury. It's a liquid at room temperature. They're usually like a silver color, right? Copper, gold, stuff like that. There's a few that aren't. They are good conductors of heat and electricity. So they allow heat and electricity to pass through them. That's why we use metal for pots and pans. They're also malleable. This is maybe a new word for some of you, but it just means that it's bendable, okay? You can hammer it into thin sheets. I can make it bend. I can take a paper clip, right? I can make it into a shape that I want it to be. It's malleability, okay? And then the last one is they are ductile. D-U-C-T-I-L-E. It doesn't have anything to do with the duck that quacks, okay? Ductile means I can pull it into a wire. So if I go to the light switch over here, okay, there's a wire that runs in the wall and into the lights, right? And so if I turn them off, there's no current now through the wire, and so there's no electricity. But if I turn it on, now a current's going through the wire and allowing electricity to flow through, right? So ductility is really something that is only for metals. Other things don't really do that. So here's some examples of metals. Some of these are elements, some of these are not. Like brass, that's something it's an alloy. It's two or more metals that are put together. Bronze the same way, steel the same way. But then you got like copper and aluminum, right? Iron. These are all elements. But look how most of them are really shiny, right? And you can see they're mostly silver colored, right? So metals, all right? Then we have the opposite. So we have non-metals. And they're called non-metals because they're pretty much the exact opposite of metals, okay? Instead of being on the left, they're on the right, okay? They are not shiny. So metals are shiny, non-metals are not. They can be various states, okay, at room temperature. Solids, liquids, and gases, okay? They have various colors. As you'll see in a minute, they have different colors. They are poor conductors of heat and electricity. We don't use these for pots and pans. And they are brittle. They will break easily if the solids. They're very brittle, okay? So here's some examples of some nonmetals. All right, I'm going to label them for you. All right, this in the top left corner here, this is sulfur. Okay, sulfur. As this one says, it's iodine. All right, this is bromine. This is carbon. This is chlorine gas. And then this is argon gas, like that guy was doing, puts electricity through it. It's pretty. All right. Then we finally get to metalloids. Okay, and metalloids are on the stair-step line, except for aluminum, like I said, which is a metal. All right, some people will call them semi-metals. Okay, and so they're pretty much in between metals and non-metals. Okay, so everything that a metal is, they kind of have some of that property. So they're like somewhat shiny. They're not really malleable, but they're also not really brittle. Kind of in between. All right, but here's their claim to fame. They are semiconductors. Okay? They only conduct under certain conditions. So if you've heard of silicone chips in a computer, that's because silicone is a metalloid and it only conducts under certain conditions. And so it's really useful in electronics because I can use heat, I can use magnetic fields to create an environment where those metalloids will conduct when I want them to, and I can turn those things off when they don't. Okay, it's pretty cool. All right, so here's just a periodic table with all the elements. Notice that most of them are really shiny metals. Okay, some of them aren't even solids, right? So some of them we can't even isolate by themselves. So it's pretty cool. All right. So that is all for this section. All right, I'll have the next section uploaded for you. Make sure you do today's assignment. All right, and if you have any questions, make sure you email me. Thanks.